So we'll quickly run through the quotient rule. Make sure you did watch the first video on the product rule, otherwise you won't be able to prove the quotient rule. So our proof for the quotient rule will start by defining just some function randomly, q of x, which I know is going to be defined as a quotient of two other functions. So here's our q of x, and again it is a quotient of two separate functions, f of x and g of x. So I'm first of all just defining the function. So first, we're just going to rearrange the function by multiplying both sides by g of x. So if we do that to both sides, we'll be left there. Now, we've just rearranged it, so I did flip from left to right, but we know that f of x is the same thing as q of x times g of x. Now, because what we can see here is we've defined a function f of x now using a product. It's q of x times g of x, so we are going to apply the product rule that you learned in your last video. Right, so left d right, right d left. So example, what we mean by that, again, here's our left side of that product, and then here is the right side of that product, which I'm highlighting in green. So left, so we just keep that left one, and then we took the derivative of the right side, and then we take the right side and multiply it by the derivative of the left side. So we just applied the product rule. Now I'm just going to replace q of x with what we defined it to be way up here. Again, this was our original definition of q of x, so I'm just going to again rewrite q of x. So I've replaced q of x wherever I see that with its original definition. Now the last step, I'm going to do a little more rearranging. In other words, I'm going to get q prime of x alone. Now why do I want to do that? Well, q prime of x, that is the derivative of our quotient function. So I want to get that alone so we can see how would I calculate the derivative of a quotient of two functions. So for our first step, we're going to subtract away the first term. So this term here is positive, so we're going to subtract it from both sides. So we have f prime of x already on the left side. And from both sides, we're subtracting f of x over g of x times g prime of x. Then we have our equal sign. And then what we're left with is g of x times q prime of x. Now I'm going to work on the left side a little bit more before I go to the right side. So there's a bunch of fractions there, so I'm going to kind of see what their denominators are. So what we're looking for is we're going to have to add this fraction with this other fraction here. What we can see is that the common denominator is going to be g of x. So I'm going to take the first fraction and multiply it on the top and the bottom by g of x. So that would be rewritten as f prime of x times g of x all over g of x. Now this other fraction is way easier because it already has the denominator. I'm going to multiply these two fractions together. So we have a minus and then f of x times g prime of x, and then g of x times 1 is obviously just g of x. And we still have the same right side of our equation. So now that these two fractions actually have a common denominator, right, they both can now be added together, or in this case subtracted. So I'm going to write it as 1. So it would be f prime of x g of x minus f of x times g prime of x all over g of x, and of course on the right side that is still going to equal g of x times q prime of x because we haven't touched that yet. So now we are going to get q of x alone by just dividing by g of x. And we know, just so it's clear, I'm actually, when I divide by g of x, that's really the same thing as multiplying by 1 over g of x. So like here, multiplying both sides by 1 over g of x. So these g of x's would cancel. So then we are finally here. This is going to be our last step, so I'm just going to write everything one more time. So we would have on top f prime of x times g of x minus f of x times g prime of x, all divided by g of x times g of x, which is g of x squared, and that will equal the derivative of our quotient function. So right there, that is our derivative rule. So just to be slightly more clear in our box here, if we have some function q of x, which is really just two different functions being divided, the derivative in respects to their common input, right? They both have to have the same input x of this function will be given by our formula that we just discovered here. So just like the product rule in the other video that you watched, there's a few mnemonic devices that we ask you to think about to help you remember these rules. So again, we started out with a function that was defined as f of x being divided by g of x, and that's a fraction. So for like our words in our language, we're going to call f of x the high part of the fraction. It's the top, and this is the lower part of the fraction. So the one that I like to use, and there's other ones you're welcome to look up, tops and bottoms, there's a lot of different words you can use, but I use highs and lows. So the little mnemonic device is right here, low d high minus high d low. Now what do we mean by that? The order of multiplication can change, obviously. So the way that I've written it, we would take the lower function. So here, the lower function was g of x. So we took that lower function g of x, and then we would multiply it according to this mnemonic device, low d high, just like with the product rule, we're implying some multiplication there. Low times the derivative of high. So the derivative of high would have been the derivative of the top function. Now I'm going to use a pink to try to say, so this is the derivative of the top function. So the derivative of the high function. Then what we have to do is we have to take the high function, so there's a minus sign, so we subtract the following product. High, so the high function, which was f of x, times the derivative of the lower function. Our lower function was g, so the derivative of that function would be g prime of x. And on the bottom, we take the lower function and we square it. So again, a very common mnemonic device that you will hear for the quotient rule. Low d high minus high d low over low squared. So at this point, you're ready to interact with the practice exercises if you want to see how some of these are going to be applied right away. So just as a check-in, remember there are two rules that you should have known right now. The product rule and the quotient rule. If you feel like you're unaware of those, I'd go back and continue to watch. Otherwise, we're going to use these moving forward. Just an interesting problem that was in the first video, in case you didn't see it. He didn't go through it, though, and he said it would be interesting to see what happens if you throw a constant there. So first of all, I want us to think back, and we kind of know a constant rule of derivatives. Now recall at the beginning of the note packet, I did tell you just some background information that I want you to use for today. The derivative of sine is cosine. So it's just a fact right now. We don't have to prove it yet. We'll get there later. We first of all kind of want you to see this as almost it looks like we're going to apply the constant rule they already learned before. So we said was like if we have some function that's really just a constant multiple of some other function, then the derivative of the function, we could just kind of pull out that constant per se, and it becomes a multiplier in front of the derivative of x. So like I would assume that this one would probably be something like 2 times the derivative of whatever sine was, which in this case I told you was cosine. So I'd assume it'd be 2 times the cosine of x, using kind of like that constant idea, but we should be able to use the product rule because this is the product of two different functions, right? We would define one function as 2 and the other function as sine of x. So if we're going to apply our product rule, I'm just going to highlight. Let's consider this the left function. So I'm going to abbreviate that with an L, and let's consider this our right function. So we're going to use our our product rule here, which is left d right plus right d left. So the left function is 2. We'd multiply that times the derivative of the right side, and as I told you, the derivative of sine is cosine. And then we'd add the right function, so the right-hand side is the sine of x. Multiply that by the derivative of the left side. So we know that the derivative of 2, what is the rate of change there as we change x? It's 0. So again, we're just tracking where we got stuff. So left is our left function. Over here, the derivative of the left side, the derivative of 2 was just 0. And then the derivative of the right, so our right side function was sine, its derivative was cosine. And over here we just see the regular right function. So what we can see here is that obviously this just goes to 0. So we're left with 2 times the cosine of x. So the product rule does jive, quote unquote, with our constant rule. So for this next example, again, we can see that we have some sort of product of two different things. So I'm just going to put in the multiplication symbol right there, just to try to emphasize. So we can see that it's t squared plus 3 is being multiplied by e to the t. So since we have a product, there's clearly two functions there. So let's call one of our functions, sorry, the input is t here, not x. Let's call one of our functions t squared plus 3, and then our other function, therefore, which I'm just going to use h of t, I'm just making up some letters. Let's call h of t to be e to the power of t. So for our purposes right now, f of t, that's on the left of the product, and then h of t, that's on the right of the product. So to apply our product rule, we know that the derivative, I'm going to use proper notation here, the derivative of our function g, so g prime of t, will be defined by the left function, which is f of t, times the derivative of the right-hand side, which would be the derivative of h of t, and we would add the right-hand function, which is h of t, times the derivative of the first function. So looking at our derivative rule, the only things that we don't have are the derivative of f and then the derivative of h, because we already do have f and t defined above. So let's just go down on some scratch work and find the derivative of f. So if f of t is t squared plus 3, we can just use the power rule there and the sum rule. So the derivative of t squared, that's just 2t. And then we already know that the derivative of a constant is going to be 0. There is no change between those outputs. So the derivative of that is just going to go to 0. So the derivative of f is 2t. And let's go ahead and find the derivative of h, because we need that in our function. So the derivative of h, that one should be nice and easy because we see that it is e to the t, and that was one that we looked at yesterday. It's our special exponential function. The derivative of e to the t is itself. So now we just got to put everything where it goes. So I'm going to restart my statement and say that the derivative of g will be found first by taking f of t, and f of t was t squared plus 3. So we'd take that and we'd multiply it by the derivative of h, which we just got to be e of t. And for emphasis, I'm going to put in that multiplication symbol so we know they're being multiplied together. And then, according to the rule, we have to add. We would take h of t, which we already know is here, And then we'd have to multiply that by the derivative of f. And the derivative of f, we said, was represented by 2t. And that is our derivative. So a quick application of our quotient rule. I'm just going to split this down the middle. Now in example 2, we're going to use the quotient rule first. So we have our low, right? Low is on the bottom, and we have our high on the top. So our quotient rule is given again, and I'm just kind of making sure we know it, is low times the derivative of the high minus high times the derivative of the low, all over low squared. So again, let's just do a little work over here. We need to find out the derivative of the high. So the derivative of the upper function, so it has an input of r, so the derivative of 3r. Just going to use that power rule. We know that is just 3. Now the low function, we would need the derivative of the low function. And again, the input of the low function is r. So the derivative of 5r squared, again, we know would just be 5. So we're going to go ahead and just use that to build our derivative formula. So we would take the lower function, which is 5r squared. So low times the derivative of the high, which we have down in here in red, which we said was 3. So low d high, I'm going to put those in parentheses just so we know that they are being multiplied. Low times the derivative of the top, and then we have to subtract the higher function, which is just 3r, and then we would multiply that times the derivative of the low, which we know was just 5. And again, to emphasize that, I'm going to put that in parentheses. And then we have to divide all of that by the lower function squared. So our lower function, again, was just 5r squared, 5r plus 2, and that's going to be what we put on the bottom, and then we have to square it. Now our only step left, obviously, is just to do a little simplification. We should clean that up a little bit. So I know what 3 times 5r plus 2 is, so that's 15r plus 6 minus 15r, all divided by, and 5r plus 2 squared. I'm just going to leave at that. I don't really need to expand that. And we can see that the r's will cancel. So our final derivative will just simply be 6 divided by 5r plus 2 squared. Over on example number 3 here, again, we could use the division rule, low d high minus high d low and all that good stuff, but I would again encourage you to try to simplify first. We can see that y is a constant factor, or a common factor in all of these, so I'm going to reduce everything by y. So if I factor out that y, so we'll be left with y squared minus 6y plus 7. Well, that's just a power rule, so, and a difference in sum rule, I guess, but the derivative of y squared is just 2y. The derivative of negative 6y is just negative 6, and the derivative of 7 is nothing. So our derivative would be 2y minus 6. Now what I also did just include on the screen was we could go ahead and use the quotient rule here. But what we're going to see again is that if we were to do that, it's just going to be a bunch of terms that all have y's in it, right? Because this y is going to go over here, there, and there. And then all of these already have y, and they're just being multiplied by 1. So we're going to see that we would be able to get the same exact answer if we did it that way too. Last one, again, just trying to see you to use what you already know. You should take the shortcut on this one, right? Y is just 5/7 times x to the negative third. So we should go back and use that most efficient rule, which is going to be the power rule. So we have 5/7 times negative 3x to the negative fourth using that power rule. So y prime would equal 5 times negative 3 all over 7x to the fourth. So y prime will equal negative 15 over 7x to the fourth. All right, so here they just want us to find when a function is concave down. And we know from our work before that a function is concave down when its second derivative is less than 0. So we do notice that our function is a product rule. We have the left side function here, which is f of x, or sorry, 5x plus 1, and we have something on the right, which we consider e to the x. So first we'd actually have to figure out our first derivative using the product rule. So the first derivative of our function f prime of x will be left times the derivative of the right, so the left side is 5x plus 1, times the derivative of the right, which we know is just itself because the derivative of e to the x is e to the x. And then we have to add the right function, which is e to the x, times the derivative of the left, and we know that is 5. So now we need to calculate our second derivative. We're going to notice that we're just going to utilize the sum rule. So we'll find each derivative by itself. But what we kind of notice here is each derivative is now a product rule. So now we are going to apply that product rule again, looking inside here. So we have a left function and we have a right function. So here, what we would do on that is that's just the original function we just did. So we already know what its derivative is, right? We just wrote it. So if we go through it again, though, the left d right, so the left is 5x plus 1 times the derivative of the right side, which is just e to the x. Then we'd add the right side, e to the x, times the derivative of the left, which is 5. So again, that is our function. But then we have to add the second part here. We got to add this part. So again, we have a left and we have a right. So we would take the left-sided function, e to the x. Maybe I can squeeze it in over here. E to the x times the derivative of the right side. So the derivative of 5 is just 0. And then we would add the right side times the derivative of the left. And the derivative of left is obviously just e to the x itself. So now I'm just going to collect some like terms, right? I have 5 e to the x's here. And then I have 5 more e to the x's there. So in total, that's 10 e to the x's. And then we know that 0 times anything is going to go to be 0. And then we have this other part here, this positive 5x plus 1 times e to the x. Continuing to simplify, we see that both of these terms have a common factor of e to the x. So our derivative will pull out, our second derivative will pull out that e to the x. We'd be left with 10 plus 5x plus 1. Now originally we were asked to find when our second derivative was less than 0. So when is this value here going to be less than 0? Well, first of all, we know that e to the x is always going to be positive. So if I'm going to multiply a positive number by something over here to get something that's less than 0, that means this thing here must be negative. So when would this become negative? Well, that's just 5x plus 11. So when is that less than 0? In other words, when is it negative? And we see that whenever x is less than negative 11/5. So whenever x is less than negative 11/5, that makes our second derivative a negative number, which means that it would be concave down. So if we write this finally as our interval notation, I'm just going to go write the answer on top. It'll be concave down from negative infinity all the way up to negative 11/5. Another very similar example to the last one, but we need to use a different rule here. So we're asked when something is concave up, so we need to find when its second derivative is greater than 0, right? Concave up would mean positive there. So first we'd have to find our first derivative of g of x. We're going to use the quotient rule. So low times the derivative of the top minus the top, or in other words high, times the derivative of the lower function, all divided by low squared. I'm going to take a moment to simplify right away. What I see is this term has a multiple of e to the x, this term has a multiple of e to the x, and this term has a multiple of e to the x. So all these terms can be reduced by a factor of e to the x. So just rewriting our derivative, we have 2x minus x squared over e to the x. So now we work on calculating our second derivative, which again we will see that we can apply the quotient rule. So low d high, so the low is e to the x, times the derivative of the top. So we'll just use this difference and the power rule. So the derivative of 2x is just 2. The derivative of x squared is 2x. So that's low d high. Then we minus. We'll subtract high minus the derivative of the low, which we know again is e to the x, all divided by low squared. And just like before, we can cancel a common factor of e to the x from all of them. So our second derivative, I'm going to simplify along the way. So our second derivative will be 2 minus, so distributing that negative again will give us negative 2x plus x squared all over e to the x, and then just rewriting it one more time so we're clear. The second derivative is going to be x squared minus 4x plus 2 all over e to the x. Now, if we're trying to find out when our second derivative is positive, we know that this thing on the bottom is always going to be positive. So the only way our second derivative would be positive is if what's on top would be positive. Now, unfortunately, that quadratic isn't like super nice to factor or anything, but you could kind of throw it into a calculator and just kind of see what it looks like. We know it's going to be something like this. So at this point, what you would do then is just use your quadratic formula to find out what are those two zeros, because we want to know when our function is positive, right? We want to say what is this x value here and what is that x value there. So if you're using your quadratic formula, and I'm going to ask you just to do that on yourself, you should get that x is equal to, and as a decimal, 3.14 approximately, and then the other zero would have been 0.58. So on both of these intervals is when our numerator here would be positive and our denominator is always positive. So our final answer, which I'm going to write, just going to erase my graph for a second. I'm just going to write it on top of that graph. So when both of these things are going to be positive, well, our first interval would go up to our first zero, so negative infinity all the way up to our first zero. Between the zeros, our parabola is negative, so we don't want that, but then it's positive again, starting at 3.414 all the way to infinity. A final good one, I just kind of like it, asks us to find just a bunch of values, just kind of again focus on our rules. So here they've defined a bunch of functions up top, a, b, and then they give us their derivatives, a prime and b prime. So down here when they write a and b, they're really referencing the functions, a and function b. So for this first one, we need to find the derivative of a times b. So I really like this again because it's just going to be some symbols. So the product rule is the first, or left, times d right, plus right, d left. And we just have all those values up top, right? So the value of a at x equals 2 is given here. If x was 2, a of x is equal to 3. B prime at 2 is 2. We would add the value of b at 2, which was just 1, and the derivative of a at 2 is negative 4. So we get 6 minus 4, which is just 2. Here they're asking us in letter B to use our quotient rule, obviously. So the quotient rule is low times the derivative of the top minus high times the derivative of the low all over low squared. So again, we're just trying to find our values. So the value of b at x equals 2, again, was 1. We'd multiply by that by the derivative at x equals 2 of a, which was negative 4. We'd subtract the value of a at x equals 2, which was 3, and multiply that by the derivative of b at 0.2, which was, again was 2 from the table, and then we divide that by the value of b, which was 1 squared. So that's negative 4 minus 6 over 1, which is just negative 10.